Okay, so right now we're going to look at chapter 25, which is charged particles, and in particular 25.1 electrons. And basically in this video I'll be talking about Millikan's oil drop experiment, which is a famous experiment in which we determine E. E being the elementary charge. E, which is 1.6 times 10 to the power of negative 19. Now this is in the modern physics section, which basically we talk about recent, and by recent I mean latest 100 years, changes in physics and developments. So E being 1.6 times 10 to the power of negative 19. So this was discovered in a time when the idea of an electron was only just beginning to become accepted. People were just starting to have this idea that there was this elementary particle which had the basic unit of charge, but no one had conclusively proven that no one knew what charge this particle had. And to do that, we'd have to find the smallest building block of charge, and that's what Millikan did. So what I mean by the building block of charge is if the elementary charge was 1, you'd be able to have multiples of 1. You'd be able to have charge of 2, 3, 4, 5, but you would not be able to have charges which are not multiples of 1, which are stuff like 2.5, 0.5, anything which is not a multiple of a basic building block would not be a possible charge. So we were trying to find basically the, in a sense, the common factor for all possible charges, which would explain to us what the common factor between all possible charges, which would explain to us what the elementary kind of elementary building block particle was. So Millikan devised this ingenious experiment to figure this out, and I'm going to go over that now. So this is what his setup looked like. So he had a chamber up here, which is basically just a entry chamber. So basically, he had this perfume bottle kind of thing going on here, which was basically like those it's basically a squeezy bottle, and what it did was it gave out a very, very fine spray of oil droplets, and this kind of fell down into this chamber down here. There was a small hole which they could fall through, and then over here, down here we have charged parallel plates, and then down here we have a microscope, and we have an eye here. Here we go. So there's an eye, and then we have charged plates here, and over here we had a source of ionizing radiation, and over here we had a light bulb, a light source, so that we could obviously see what was happening. A light source, and then okay, so this is what's happened, and then over here we have a charged plate with a variable voltage across it. So this had a variable voltage, and this is a very, very ingenious kind of setup, which kind of let Millikan figure out the elementary charge of an electron. So what would happen here is basically he would spray this oil droplet. Some of the oil droplets will fall down, and then this ionizing radiation, what would happen? It would ionize the gas in this chamber here. So this chamber already had lots of electrons floating around. And when the oil drops fell down, they would kind of pick up the electrons, and they would gain a negative charge. It could be 1 electron, it could be 100 electrons, who knows. But anyway, they would gain a number of electrons, and they would gain a charge. And what would happen is there's basically two forces acting here. One which is a gravitational force, which I will draw in a different color, which is, as you are probably very familiar, mg, and the other is the electrical force, which is up here, QE. Okay, so what he was trying to do is he was trying to find an equilibrium position. That is when the oil droplets are actually able to kind of float in mid-air, and he would watch them through the microscope to make sure they were floating by mid-air. And he'd do this by fine tweaking this until he gets a voltage at which the upwards force is equal to the downwards force of gravity. So what he did, so basically by doing that, you would get this formula here. If your QE would be equal to mg, and what is E? We know E is V over D, so Q V over D is equal to mg, and over here, we're moving the formula over here, it would be Q mg d. Q equals mgd over V. And I mean, this is quite simple. V we've controlled because we're obviously just turning a knob which sets V. G we know, D we know because that's just a separation between these two plates. And M, the mass of our oil droplet, we can actually work out because the oil droplets have uniform density. So by looking through a microscope and measuring the radius of these oil droplets, we can work out its volume and then we can work out its mass. So by doing this, by finding the voltage at which the force of electrical attraction is equal to the to the gravitational force, we can figure out the charge for each oil droplet. And then what he does is he goes and does this thousands and thousands of times and gets all these numbers, and then through this through a bit of complex mathematics, you can find a common factor of all your numbers, and then he found that number, which was 1.6 times 10 to the power of negative 19, and this fit for almost all his data. There's a little bit of a corruption kind of charge going on here, where Millikan was later seen to have accidentally discarded a lot of data that didn't agree with this to increase his percentage, his accuracy basically. But that's another matter entirely. But this is basically how his experiment worked. And basically the principle was he ionized this gas chamber, and he gave the oil droplets a charge, and then he made it so he fiddled with the voltage until there was a point where he looked at an individual oil droplet, figured out its mass, and then already knew gravity, distance, and voltage. And he fiddled with the voltage until he got to a point where the upward electrical attraction force was equal to the force of gravity, and from that you can work out the charge by equating these two forces. But the really interesting thing is he figured out that there was a force of air resistance as well. And what he did was he actually watched the oil droplets fall first without the electrical field on it all, and then he worked out the force of air resistance, and he accounted that in as well. So he was a very smart man, and he worked out all the kind of anomalies or things that might cause error, and that is the mark of a really, really good scientist with excellent scientific practice. But what we basically need to know is, that's a nice fact, but you have to know that he did in fact watch this experiment with the voltage off first, and then he watched it with voltage on to account for the air resistance falling. But you have to know that the basic principle is that the electrical force is equal to the gravitational force. And then he got a whole bunch of data, thousands of data points, and found common factors from it all using mathematical methods. And he found that almost all the data points, minus some experimental error, were multiples of this number here, 1.6 times 10 to the power of 19. And this was done a long time ago with just a microscope and light. And it was found that his result was very, very accurate for a true value. It was something like only a couple percentage off the real value, which we've just been repeating the experiment over and over again with much more advanced technology, and we still get the same kind of result. So Millikan's experiment was really excellent, and this is how we found out the elementary charge. And this kind of conclusively proved that there was an elementary amount of charge that was indivisible. So there was whole amounts of charged particles. There was this charged particle called electron with this much charge, and charge is a discrete value, and that's what this whole experiment proved. So I hope you enjoyed my video, and I'll see you in the next one.